So I want to challenge you right off the bat with this question. What does the word ground actually mean to you? When you say it out loud, what physical object are you picturing in your mind?
Because honestly, a ground can mean an 8-foot copper rod driven into the earth to protect a building from lightning. It could be the green safety wire in your AC power distribution system. Or it could be a reference plan on a high-speed printed circuit board. It could even be a tiny narrow trace providing a return path for a low-frequency analog signal on a satellite. The engineering requirements for each of these physical realities are completely different. So, from this moment forward, we have to strictly categorize them into two distinct buckets: safety grounds and signal returns.
Moving on to Section 2, Safety Grounds and Faults. Let's look at that first bucket and examine the macro-level anatomy of a facility branch circuit.
Take a look at the explicit layout of a properly wired standard 120-volt AC power distribution branch circuit. We have three distinct conductors here. You've got your hot conductor in black, your neutral in white, and your ground in green. Now look really closely at the service entrance panel on the left. Notice how the neutral and the ground are connected together at one and only one point in the entire system? That is absolutely crucial. To do otherwise would allow normal load current to return on the green ground wire, which creates a dangerous voltage drop. The only time that green ground wire should ever carry current is during a fault condition.
And here is exactly how that fault mechanism works. Think of the safety ground as a massive emergency pressure release valve. First, a short circuit fault occurs. Say, a frayed hot wire touches the metal chassis of a washing machine. Second, massive fault current instantly travels via that green ground conductor straight back to that single neutral bond we just saw. Third, this sudden surge in current causes the overcurrent protection device, your circuit breaker, to trip, instantly cutting power. This low impedance path clears the fault safely and quickly. If that path is broken, the chassis stays energized, and the very next person to touch it, they literally become the path to ground.
Section 3. Calculating ground conductor impedance. To really understand how this safety mechanism happens, we need to look past the surface and dive straight inside the material to the microscopic math. Okay, this is where the engineering truly begins. If we want a perfect return path that doesn't generate electromagnetic noise, we need a transmission line with the lowest possible characteristic impedance. We call this Z0. Typically, we want this to be 1 ohm or less. The math, as Henry Ott details, proves that to get a low Z0, a transmission line desperately needs high capacitance and low inductance. Notice how parallel flat conductors mathematically achieve this far better than your standard parallel round wires.
Let's break this mathematical expression down completely, step by step. Z0, our characteristic impedance measured in ohms, equals 377 divided by the square root of ER, all multiplied by H divided by W. What does this physically mean? Well, 377 is a constant. It represents the intrinsic impedance of free space. The ER in the denominator is the relative dielectric constant of your insulating material. I want you to think of a dielectric's atoms like a massive crowd of tiny rubber bands. When an electric field hits them, they don't conduct electricity. Instead, they stretch and polarize, storing massive amounts of capacitive energy without shorting out. A higher dielectric constant means more stretching, which increases capacitance, which mathematically drives our Z0 impedance down. Then we multiply by H over W. H is the height, or the separation distance between the conductors, and W is the width of the conductors. Let's do a practical walkthrough right now. Let's say you're designing a PCB. We're using standard FR4 fiberglass. That has a dielectric constant, ER, of exactly 4. Let's say the distance between our signal trace and our ground plane, our H, is 0.1 millimeters. And let's make our ground plane super wide, say a width W of 10 millimeters. Plug it in. The square root of our dielectric constant, 4, is 2. So 377 divided by 2 gives us 188.5. Now for the geometry. Our height of 0.1 divided by our width of 10 gives us 0.01. Multiply 188.5 by 0.01 and boom, our characteristic impedance Z0 is 1.885 ohms. Look at that relationship. If we want to drop that impedance even closer to 0, we just maximize W, making it a massive flat plane, and we minimize H, squishing the conductors as close together as physically possible.
And this brilliantly illustrates the real-world implementation of that exact math. What you're looking at is a zero-signal reference plane, or ZSRP. By creating a massive, flat, uninterrupted metal plane right beneath our equipment, we have mathematically maximized that width W to the absolute extreme. All our cables and signals are routed flush against it, minimizing the height H to the extreme. The physical result is a mathematically optimized ultra-low impedance ground structure.
Section 4. Signal grounding and topologies. Now let's shift gears and apply this math to practical signal grounding topologies for our electronic equipment.
When wiring up systems, engineers generally choose between single-point grounds and multi-point grounds. Single-point grounding is great for low frequencies, but as your frequency increases, the stray capacitance between wires and the metal chassis starts acting like invisible short circuits. This basically forces our system into becoming a multi-point ground anyway, whether we want it to or not.
Even within single-point systems, you've got two choices. On the left is a series connection, often called a daisy chain. Sure, it's incredibly easy to wire, but it is absolutely terrible for electrical noise. The noise current from circuit 3 has to flow right through the ground wire of circuit 1, directly coupling their noise together. On the right, we have a parallel or star connection. Here, each circuit has its own dedicated path to the single point. This neatly avoids that common impedance coupling, making it vastly superior for noise control, even if it does require a bit more copper wire.
All right, Section 5, the quiet ground myth. This is the gotcha segment. We are now arriving at a common pitfall that doesn't just fail to work, it's actually incredibly dangerous and completely illegal. So many engineers mistakenly believe that connecting their sensitive electronic system to a separate, isolated ground rod out in the dirt will somehow give them a magical quiet ground totally free of AC power noise. Listen to me. This violates the National Electric Code. Look at the fault path here. If a fault occurs, the massive current has to travel down your quiet ground rod, force its way through the physical dirt of the earth, back over to the utilities ground rod, and finally up to the neutral bond just to trip the breaker. But the earth is incredibly resistive. Trying to clear a massive fault current through the dirt is literally like trying to drain the entire ocean through a clogged pipe. The current just won't flow fast enough to trip the breaker, which means your equipment enclosure remains lethally electrified. Let's rapid-fire debunk these three massive myths, straight from Henry Ott. Number 1. The Earth is a low impedance path. False. The impedance of dirt is orders of magnitude greater than a simple copper wire. Number 2. The Earth is an equipotential. False again. Because it has such high impedance, any current flowing through it creates massive voltage differences across the surface. And number 3. Conductor impedance is determined by its resistance. False. Remember the mathematical derivation we just did? We proved mathematically that impedance is heavily dictated by inductive and capacitive reactance. Copper conductors that are dynamically shape-optimized to lower inductance will always beat the dirt. Finally, Section 6, Essential EMC Takeaways. Let's transition into our rapid-fire summary to lock in these critical rules. These are the 3 golden engineering rules you must never forget. Rule number 1, AC power grounds, that green wire, are strictly for clearing safety faults. They are highly polluted with noise and make absolutely terrible signal references. Rule number 2, any conductor longer than 1/20th of a wavelength of your operating frequency instantly ceases to be a low impedance path. It mathematically becomes an antenna. And rule number 3, to truly kill noise, you must use flat metal planes, placed as close as physically possible to your signal traces to minimize that Z0 characteristic impedance. So, I leave you with this final, provocative thought. When you are laying out your very next high-speed circuit or industrial facility, is your design going to rely on the dangerous illusion of connecting to the dirt of the earth, or will you engineer a mathematically proven zero-signal reference plane? If you want to continue mastering the physics behind professional electronic design, hit subscribe for more EMC and automotive communication protocol survival guides. Thank you for joining me on this explainer, and I'll catch you in the next one.